Hello, my dear students. I want to explain about atom and atom structures. So today, make it very easy for you. If you remember, each atom diagram was like simplified as a nucleus and the shells around it. So each shell actually is an energy level, and its energy level is different from the others. When you go to the next shell and next shell, the more you move from the nucleus to the outer part and you make a distance from it, so the number of the shells increases, so their energy level also increases. So each shell has a number. This is the closest one to the nucleus is shell 1, the second shell, and then third shell, the fourth shell, and so on. So now instead of using shell 1 and shell 2 and shell 3, this shell number we can use instead principal quantum number. So we don't write principal quantum number. Instead we can put a symbol as n. So n shows principal quantum number of the atom, and each principal quantum number equals to the shell number. For example, the principal quantum number of the shell 1 becomes n equals to 1. For the second shell becomes n equals to 2. For the third, n equals to 3. For the fourth becomes n equals to 4. So n, or the principal quantum number, shows actually the shell number. Do you remember how we could, how many electrons, maximum number of the electrons each shell can hold? You remember that the first shell, maximum number of electrons that you can put on the first shell is 2, and on the second shell for you was 8, you remember? And we in the year 10 and 11, we make it very simple, and we said that the third and the fourth also they take 8. But here, actually it's not like that. So easily now, by knowing the principal quantum number, you can calculate the maximum number of the electron each shell can hold. How do you do that? So this is the formula. Maximum number of the electrons each shell can hold equals to 2 times n squared. Okay? Now, I give you an example. On the first shell, shell 1, the maximum number of the electron that it can hold 2 times. This is the principal quantum number, n power 2. So this one becomes how much? 1 times 1 times 2 becomes 2. So the maximum number of the electron that it can hold is 2. For the shell 2, you also calculate for the shell 2, how many electrons, maximum number of the electron it can hold? 2 times 2 squared comes 8. Why, right? For the shell 3, can you do that? For the shell 3, 2 times, and instead of n, we put 3, power 2. Becomes 18. 3 times 10, 3, and times 2. For the shell 4, the same. Becomes 2 times 4 squared becomes 32. So on the shell 4, the maximum number of the electron that we can put is 32. On each shell, we have subshells, okay, that you cannot see here. Subshells. We have here on the same shell. For example, shell number 1 has subshells. Shell 2 has subshells. We have different types of the subshells. They are called as S, P, D, F, G, H, I, N, but for U up to F, you need to know. Each of these subshells that you see here, they have different shape, and the shape is different from the other subshell. S is a spherical, is a rounded shape, and it's only one type of S subshell we have. This is called one orbital. Okay, so we have shells, we have subshells, and each subshell has orbitals. S only have one orbital, one type. Each shell has one s orbital. But when you move on from shell 1 to shell 2 to shell 3, these orbital size of the s changes and become bigger. So this is s orbital in the shell 1, then in the shell 2 it becomes a little bit bigger, in shell 3 a little bit bigger, and continues. So what is changing in each shell about the s orbital is the size of the s orbital. Okay? But you have always in all the shells one s orbital. Okay, so imagine this is the atom nucleus, and this is the first shell, second shell, third shell. So on the first shell we have only s orbital. On the second shell we have one s orbital. We have p orbital. On the third shell we have s, p, and d orbitals. On the fourth shell, we have S, P, D, and F orbitals. You understand this? Now, each of these subshells that you see here, I said they have their own shape. So for the S, it was spherical, round, and when you move on and to the next shell, it becomes bigger only. But for the P orbitals, we have 3 p orbitals, 3 types of the p orbitals. So how many types do we have? 3 of the p. How do they look like? They have different shapes. I can show it to you. Why do I need to put these shapes on the coordinates, showing by these lines and axes and coordinates? Because I want to show the 3D shape into the space. Because their orientation and direction into the space and the 3D shape make a difference. If I want to show on 2D, doesn't make any difference. So you have to imagine that on the y-axis and the x and z into the space, how they are actually, their position are relation to each other. So this is P, one type of the P. This is the second type. And the other one is like a dumbbell. Okay? So there are 3 different types of the p orbitals. 1, 2, and 3. They look like a dumbbell. Okay? When we move on to the next orbital, the shape of the orbital becomes harder. So only have to know S, P, and D orbitals. For the D, we draw the coordinates again. This is Y, this is X, and this is Z. And so this is 1 dumbbell, 2 dumbbell, and then the next one on the X axis. So this is actually the shape of the D orbital. How many D orbitals do we have? For the orbital D, we have 5 types of the D orbital. So, make it easy to understand. S orbital is only 1 type. We can show the S orbitals by actually a box like this, and we put the electron inside it. So it has one square box like this. For the P orbitals, there are 3 types. 1, a square box, 2 square box, and a 3. So we show the different orbitals of the p by these square boxes. How many? 3. For the d, we have 5 types of the d orbital. 1, 2, 3, 4, and 5. For f orbital, we have 7 types. 1, 2, 3, 4, 5, 6, and 7 times. And of course, for the G, we have 11 and so on. Each of these boxes that you see, or orbitals, they can hold up to maximum 2 electrons. They can hold up to 2 electron maximum. First, like this. You show the electrons by an arrow, one upside, and the other one should be in the opposite direction. Why? Because the electrons, they have similar charges, they are in the same energy level, and if you put them in the same direction, they will repel each other. Okay? They stand away from each other. So this is wrong. They have to be in the opposite direction, so they make a spin movement. To show an spin or movement. For example, if I want to fill the p orbitals by electrons, if I have electron, I put it here. If I have more electrons, I don't place it here. I don't pair them first. I first fill up each singular or individual orbital, and when I finish with it, and I have electrons to put in the same orbital, or move on and pair them like this. So once all the orbitals are filled up with the electron, 1, 2, 3, 4, 5, 6 electrons on the p orbital maximum. So what should I do? I should go to the d orbital. I cannot move on anymore with that. So I go to the d orbital. 1, 2, 3, 4, 5. When finished, I come back and pair them up. Once finished, you move on to the next one, next orbital. First singularly filled up, then you go back and pair them up. Okay? So look at these orbitals. How many orbitals we have in the S? We have 1 orbital, one square box, 1 type of the S orbital we have. How many maximum electron we can put in it? The maximum number of the electron that S orbital can have is 2 electrons. How about the p orbital? The maximum number of the electrons that we can put in the p orbital is 1, 2, 3, 4, 5, 6. So it's 6. And for the d orbital is 10, because it's 5 times 2. And for these 7 orbitals, each they take 2 electrons in pairs, becomes 14. And it continues like this. Okay? I think I can show it by this table is better for you to understand. So imagine that we have this table. I want to show that first of all, each shell 1, shell 2, shell 3, shell 4, or these are the principal quantum numbers, or n, they take, I can put n, now you know what n means, principal quantum number. Each of them, they have 1 single s orbital. What are the different types of the orbital presenter? A maximum number of the electrons we want to show you on this. So each of them, they have 1 s orbital. S. I don't put more s because s is only 1 type, I told you. So each shell has 1 s orbital. The first shell of the atom, it carries only maximum number of 2 electrons, and it cannot be more than that. So you know, each of the orbitals in the s orbital, maximum number of electrons that you can put in the s orbital is 2, isn't it? So the first shell only has 1 s orbital and not more than that. the one type of the orbital it has is s. This from the second shell, another orbital is added, which is p orbital. And I told you that a p orbital has how many types? 3 types. 1, 2, and 3 orbitals of p. They present in the second shell. In the third shell, we have 3 p orbitals, 1 s orbital, and we have 5 d orbitals. 1, 2, 3, 4, and 5 d orbitals we have. Like this. Because d has 5 types. P orbital 3 types, and s is only 1. Okay? So till now, if you want to calculate the maximum number of electrons on each shell, s carries 2. You know that the s orbital carries only 2 electrons in opposite spins. Okay? So what does that mean? It has maximum 2 electrons on the first shell. On the second shell, how many electrons do we have? 2 on the s orbital. I want to show you like that. P2, and another 2 in this orbital. How many overall? 1, 2, 3, 4, 5, 6, 7, 8. Maximum 8 electrons. So here it takes 2 electrons, 2, 2, 2, 2, 2, 2, 2, 2. How many orbitals do we have? 1s, 3 p's, and 5 d's. So becomes how many electrons overall? 18. For the next one, on the fourth shell, we have 1s, 3p, 5d, and 7f. 7f, each f orbitals take 2 electrons in the opposite spins. Becomes 14 electrons plus p, each takes 2, and d 2, 10, 6, 18, and this one, how many? 32 electrons maximum. It's like this. 1 s orbital, it has 3 p orbitals, it has 5 d orbitals, and it has 7 f orbitals. So overall becomes 32 electrons on the fourth shell. So I want to tell you now the rules for filling up the atomic orbitals. How do we fill the atomic orbitals? It's like that. The orbitals that they have lowest energy, they have to be filled first. Based on an energy level, S has the lowest energy, then is P, then is D, then is like F, then G, and like that. But there are also exceptions for that I will mention to you. There are only 2 or 4 elements that they are not following the rules that I'm mentioning to you. The next one is that each actually orbital can only have up to 2 electrons, but these 2 electrons needs to be in opposite directions. They cannot be in a same direction like this. Okay? And if you have orbitals with the same energies, like for example, this is the p orbital, it has 3 orbitals here, the p subshell, and 1, 2, 3 orbitals it has, so each should take 2 maximum electrons. But if you want to fill up this one first, you have to put first one here. You have more electrons in the p orbital, you have to put in the second orbital and the third. Then if you fill up all, you go back and pair them up, but it should be in the opposite direction, not in the same direction. Okay? So I give you an example. For example, I start with the hydrogen atom, which has only 1 electron. Okay? So if I want to write this for the hydrogen electron, or the hydrogen atom, the electrons for that, we know that this is the actually how it look like. This is the a nucleus, and there is one electron on the first shell. So we know that, so first shell, it has only, how do I show? It has only one orbital, which is S, and I show it like this, the square box. One orbital, and it has one electron. So I put one electron in the S orbital and no more. How do I write it? I should show that this S, because all the shells, each shell, they have S orbital. So I should know this S orbital belongs to which shell. How do I show it? I put the shell number here in front. First shell, S orbital. Now the number of the electrons that we put in the S orbital, how do I show? I'll put it in here. 1. So this one shows, this number shows shell number, or that N, I mean the principal quantum number, you remember? And this number or figure here shows how many number of electrons in the orbital. How many? 1. Now let's do this with the helium, which has 2 electrons. Okay. So the next element was helium with 2 electrons in the atom. So this is the diagram, electronic configuration of this, and 1 electron here and 1 electron here. So it has 2 electrons. How do I show this? So the first shell, it has 1 shell only, isn't it? It has only 1 shell. So on the shell 1, it has 1 box, and which is S orbital, isn't it? The S orbital on the first shell, and it gets 2 electrons. 1, 2. This is how I show it. I cannot put more because that's S orbital. Okay, S orbital is only 1 type. If you have more, you have to go to the next shell. Now, lithium has 3 electrons. And 3 electrons means 2 electrons on the first shell, 1 electron on the second shell. So it has 2 shells. So shell 1, and shell 2. On the shell 1, it has S orbital only, and the shell 1. And how many electrons I can put on it? 2. 1, 2. I have 1 more electron. I cannot continue here because the first shell only take 1 S orbital and no more. Then we go to the second shell. On the second shell, we have, yes, again, I said each shell starts with the S orbital. So this is the S orbital on the second shell. How many maximum I can put on it? 2. But if I put 2, becomes 4 electrons. I need only 1 more electron is left. So 1. So how do I show it? Like this. 1, 2, 3. So this becomes 1s2 and 2s1. The electronic configuration for lithium. Now for beryllium, shell 1, it has 4 electrons, huh? So this is the diagram, 1, 2, 3, 4, isn't it? 4 electrons it has and 2 shells. So 1 shell, this is the shell 2. On the shell 1, we have only 1 s electron, 1 s orbital, and on the shell 2, we have s orbital. I'll put it this side. S orbital. Okay, let's see. So at the s orbital, I put 2 in the opposite direction. So I have still 2 more electrons to go. So what should I put? I cannot continue with the shell 1 because shell 1 only take one s orbital. I go to the next shell, which is s. This is second orbital. So I put one electron here and one here. Now the s orbital is filled up. If I have more, what should I do? Another one. Now what we do for boron. Boron, this is the nucleus. 1, 2 electron. 1, 2. 1, 2, 3. So it becomes all 5. So it has 2 shells like this, but it has 5 electrons. So 1, 2, exactly the same thing we do. Shell 1 s orbital, shell 2 s orbital is done. But now we have one more electron. Where should I put it? On the second shell, we have another orbital. We call it p, which has 3 boxes or 3 orbitals, different orbitals. So where should I put the next electron? In the p orbital. 1, 2, 3, 4, 5. Lithium, beryllium, boron, and then is carbon, 6. With the 6 electrons. So it means that another electron is added. Where should I put it? Here? No, I cannot pair it up. I put it in the next box, in the next orbital of the p orbital. But the same shell, second shell, because it has 2 shells still. Right? So, what is the next element? Nitrogen, with the 7 electrons. So, I put another electron here. So it becomes, still we have, that element has 2 shells, the atom, but it has 7 electrons. So let's count. 1, 2, 3, 4, 5, 6. So another one. Should I put it here? No. Should I put it here? No. Here? Yes. So now all 3 boxes, or the 3 orbitals of the p, have one singular electrons. It means it's filled up half full. So the next element is oxygen, which is 8 electrons it has. So we put another electron here, becomes 8. So it has 2 shells, as you can see. So but one more electron. 1, 2, 3, 4, 5, 6, 7, 8. Where should I put? So I have to start pairing them up. So I put it here in the first box of the P. Oxygen. Then we have F. Fluorine. 9 electrons. I put another one here. So still it has 2 shells. 1, 2. So but one more electron. So I continue like this. So fluorine, when we have neon, neon is 10 electrons. We put the electron here. So still it has 2 shells, but the last shell is filled up, is very stable. So 1, 2, 3, 4, 5, 6, 7, 8, 9, another electron in the opposite. Now, the p orbitals are all full. On the second shell, I said we only have 2 orbitals, s and p, so we don't have d. So if you have more electrons, you have to go and move on to the shell 3. Shell 3 also starts from s orbital. Now look at here. Shell 1 for the sodium, it has 1 more electron, but it has 3 shells now. So 1, 2, 3 shells. The first shell is only s orbital. Okay. For the second shell, we have s, we have p, all full, isn't it? So this is 6 and 2 becomes 8, 9, 10. So another one, I need to have another 1 more electron to go. So I move on to the third shell. The third shell also starts from s orbital. Start filling it up first, like this. Sodium. The next, magnesium with 12 electrons and with 3 shells. So how should it has 1 more electron compared to the compared to the sodium. So I need to put one more electron here, add one more. I cannot put it here, no, this one also filled up. The third shell is, s orbital is half full, so we need to continue with filling it up. This is the diagram. This is the electron configuration, and the boxes of the orbitals on each shell for the magnesium. So after magnesium, what do we have? We have aluminum with 13 electrons. Aluminum with 13 electrons. This is 12 electrons. So we need one more. I cannot put it on the s. I should move on to the p orbital. So how should I place it there? I put one on the first orbital in the up direction. Okay? So after aluminum is Si14. With the 14, one more electron. I need to put here inside this diagram. So I continue with filling up the next orbital. Phosphorus has 15. One more electron, and we put it in the P. And it's very easy, you see? So the next one is the sulfur. 16 electrons, so you have one more. What should I do? This one is half full, so I continue with pairing the electrons up in each orbital. I put it here. The next element, chlorine, with 17 electrons, so I put one more here. Correct? Look at argon with one more electron and 18 electrons, so I have to pair this last orbital. So you see this one also is filled up completely. So that's why they say argon has the full electron shells. So the last shell is completely filled up with the maximum number of the electron that it can have. So in the shell one, we have one more type of orbitals. What is that? Is D. How many types it has? How many different types of the D orbital we have? We have how many? 5. 1, 2, 3, 4, 5. Now, the exceptions start from here. This is very important. Notice, as I said, up to this actually element, argon 18, with the 18 electrons. So you see that everything, the rules are, everything is like this. But when we reach to the potassium with 19 electrons, okay, atomic number is 19. What happens here? Actually, it doesn't follow the rule because the s orbital in the shell 4 is lower in the energy than the d orbital in the third shell. Okay, it's compared to these two. When you make a comparison, the energy level of the s orbital in the fourth shell is lower than d orbital. So it should be filled up first, not this one. Once this one is filled up and completed, you can continue with filling up the d. So for potassium 19 electron. So we have 18. We need to put one more electron. We put it here, not on the d orbital. Okay, and for next one is calcium 20. So for the calcium 20 with 20 electron, we should fill up s first, put another electron in opposite direction. So you see that still the d orbital in the third shell is empty. Once you finish with that, you can start filling up the d orbital, starting from scandium. So SC 21. Okay, this is the way. The SC21, okay, we put one more electron in the d orbital in the third shell. The next one is titanium Ti with 22 electrons. So what should I do? I just start filling up the d orbital on the third shell. Then we have vanadium, V, which is 23 electrons. So we need to put one more electron here, okay? this is now very important. The d orbital, when the d orbital is half full, what does that mean? It means that all the orbitals of the d are filled up at least with one single electron. It is more stable and it is more preferred. So if now you have to, actually if you have electron, first you have to make it as a stable element. The diagram should be stable. So you have to, if it is half full, so this is much more preferred. And also the same case happens when it is completely full. All the d orbitals, they get paired electrons in their orbital. Okay, so we have to make sure that we have these two stable forms. Another exception is here. This is very important that you have to notice. Chromium 24 with the 24 electrons, one electron more than titanium. Okay, so what should I do? If I put the electron here, you see, I put the one more electron here. It means that it needs only one more electron to become stable. So even if you do that, this actually electron from here jumps into this by itself. So we put one more electron here, and the other electron moves from the s orbital to the d orbital to make it stable. This form because it's very stable. Okay, so that's why this is what you get for the electronic diagram of the chromium 24. So one electron from the s orbital goes into the d orbital to make it more stable. Then after this, again, you continue, put an electron first inside the s, then move on pairing the d up. Okay? So for Mn25, magnesium, you have to put the electron here first. The priority is with the s. Okay. So after magnesium we have iron, Fe26. 26 electron. We have one more. What should I do? I start now pairing them up. It continues with the cobalt 27. One more electron. I pair the next one up. The next one, nickel, and I with 28 electrons. I put it here. Again, 3 orbitals of d are filled up. The next one, if I want to put, what happens again? Yes, you can make it all completely full and make it more stable. For the next element, which is copper and 29 electron, I need to put one more. I can put one electron here, but you see, if all it needs one electron to become stable, so I remove this one from here and put it here. So another exception, S has only one electron in the s orbital. That one moves here. So again, with the next electron that you want to draw, and it is zinc, Zn. It is Zn 30. You need one more electron, you put it here. First fill up this one, then continue filling up the P on the fourth shell. Am I right? Very good. So for the zinc element with the 30 electrons, this was how the orbitals are set up with the electrons. So now we want to write in another form electronic configuration for the zinc element. So as you can see, in the first shell, s orbital in the first shell, we have how many electrons? 2. Then in the second shell, s orbital, we have 2 electrons. In the p shell, in the second orbital p shell, we have 6 electrons. Then we continue with the third shell s orbital, 2 electrons. Third shell p orbital, 6 electrons. And the third shell d orbital, we got 10 electrons. And in the fourth shell s orbital, we got 2 electrons. In a shorthand, if you want to write, to make it simpler, to avoid writing too long, what we can do, okay, we say that this is the electronic configuration for argon, which has 18 electrons, isn't it? So we write Zn30, the electronic configuration in a shorthand becomes argon. And what is left here, this is 3d with 10 electrons, 4s with 2 electrons. This is the shorthand form for writing the electronic configuration for the element zinc. You can continue with the rest of the element, writing down like what we have done exactly. And if you have problem, you can ask me. But let me show you about the priority of the elements and how orbitals, when you want to fill them up with the electrons, you can use this diagram too. You can use this diagram, and it shows you the order of filling up the orbitals with the electrons. As you can see, moving down, first is the 1s, after that is 2s, then 2p, then 3s, isn't it? So again, you start with 3p, the priority is first 4s, and then you go to 3d, then 4p. So when you want to go and do it for the next element, you can, if you had problem, you can also look at this diagram and refer to this one, okay? Thank you.